Okay, hello everybody. How's everyone doing? All right, it's September already. Us working people, we had a long weekend this weekend, which was great. You don't get many of those, so it's good to have a long weekend. And now here we are back at it. All right, so first of all, any questions on anything? Any topics? I did get an email from IT. They merged all the sections into one section. It should be relatively transparent to you. But since there was like 6 sections, it makes things easier for me to just go to one place. So again, should be no action required on your part. But if you got that notice, that's all they did is just collapse all the sections into a kind of this master section. So that was done today. Okay, I do have out there now the project description. I'll spend a little bit of time later on going over that. Also, some homeworks are now out there. Since I did post them late, you'll notice that the first one isn't due till next week, right? Class 3, because I did post those a little bit late, so that's fine. The first one will be due next week. So we'll go over those briefly as well at the end of the class today. Okay. All right, so again, all the notes are out there. I was just going to pick up from where I left off last week. We were I finished on this. We were talking about system constraints. Remember this? When you're first trying to scope the project, the problem, you need to first identify the problem, be able to clearly iterate what is the problem you're trying to solve, and then once you identify the problem, we talked about you have to root cause the problem, understand why the problem is there. Many times people can try to jump to a solution, or the customer will come to you and try to tell you a solution without really understanding the problem. So one of the first things you do when a customer comes to you and says, hey, I need you to go do this thing, they may be telling you actually how to implement a solution rather than explaining to you the real problem that they have. So you always want to, when that happens, you always want to step back a little bit and try to understand what the true problem is, because most times they're trying to tell you how to solve a symptom of a problem. Okay, so then you root cause it. So identify the problem, root cause it, Pareto rank it, because we probably won't be able to solve all aspects of the problem because of constraints like this. I'll talk about this in a second. And so you have to Pareto rank it, solve the biggest parts of the problem, first. We talked about identifying stakeholders. There's direct and indirect stakeholders. Draw the system boundary. And then step 5 was really this one, identify system constraints. Remember I said a system constraint is anything that limits the degrees of freedom and how you can implement a solution to the problem. And you have to know these early on, because if you don't have an accurate understanding of the constraints, you're going to end up making decisions about how to, which requirements to include, et cetera, that may not map well to the constraints you're under. So for example, schedule and resources. I point to this one first because it's always there. There's always schedule and resource constraints, and you may not be able to implement everything you sign up to because of some constraints. Let me give you a couple examples. Digital cameras. I think I mentioned this one before. For a digital camera to go into Best Buy over Christmas time, that product has to be finished by April, because the rest of the year is just spent getting it into the supply chain and getting it out. So your software can't arrive in May or June and then still try to make it. If you miss April, you're done for the next year. Okay, so you can't. So if you have a schedule constraint, you can't sign up for more requirements than you can deliver in that time frame. Okay. That's just one example, but things like that happen all the time. And so these constraints are there to help you bound, just what you can and cannot do. So at the top, I think I went through a few of these, but just as a refresh, I'll pick one from each category. System constraints. many cases, you're going to be told or dictated or have to support a certain operating system or a certain number of operating systems. In my line of work, most of the software I ship is on Linux, and there's certain versions of Linux that are hardened or that a customer is on. Customers don't always jump Linux versions every day. They pick one, they stick with it for a long time. So they may say, listen, if you want to bid on this project, you've got to support this version of the Linux operating system, for example. Environmental, we talked a little bit about that. Security is a big one there. It's becoming really a big issue across a lot of products. These smartphones are starting to become a target for hacking. A lot of security related legal rules pertain. For example, security in the U.S. Is different than the security requirements in Europe, so you have to understand those. That could be a constraint as well. Economic, I talked about the licensing issues I think last time. You have to be very careful with licensing, especially with open source software. Political. There is a lot of politics in organizations, not just politics like in governments, but that political statement is more about interdepartmental issues where how you solve the problem and what you solve may be, quite frankly, dictated by the organizational politics within the company. That actually happens a lot. And it's very deep in some cases, so you have to sometimes understand the internal politics when you're signing up to do certain things. For example, if one site or one group in your company feels like they are the expert in one area, then trying to go in and do work that they would view as theirs, quote, that they own, would cause a lot of internal strife. This really happens in the workplace. You have to be very cognizant of this. Normally, if you're just an individual contributor, you don't have to worry too much about internal politics, but as you start managing people, it becomes more evident. And then technical, there's a lot of technical issues as well, choice of different technologies and things like this. So there's a lot of these constraints that exist always. You have to identify which ones are important to you for your project, and then understand what that means to the degrees of freedom you have to implement a solution. Remember, when you're designing software, you probably, it's from requirements to design to implementation. It's a one to end mapping, right? Oops. So multiple designs can be used to implement a requirement, and same thing with implementation. So what we're trying to do by understanding the constraints, it helps limit the number of options you might have as you go through the life cycle. So that's kind of what's going on there. Okay, so let's talk about this next topic. I want to talk a little bit about functional and non-functional requirements, just to make sure we understand what this means, because they're actually quite different, and some of these are harder than others to actually specify properly. Functional requirements, basically, most simplistically, is what the software has to do. Non-functional would be how well the software has to do it. Think of the difference. That's the key difference. So functional is the key features that the software will provide. When we start identifying functional requirements, and I've got a set of slides I'm going to post. I don't lecture on it anymore because it's kind of dry, but it's a lecture on how to write good requirements, good functional requirements. I'm going to post that because part of your project, I'm asking you to write some requirements, and although I'll talk about some tips and tricks, I'm going to post some extra material for how to do a good job writing them. But so I'll get to that, how to actually write natural language requirements later. But functional is more about the features. They have to be traceable from the very beginning, and the way we're going to do it here is we'll start off by when we get into the modeling section, talking about how to design use cases and misuse cases, and tracing requirements to those use cases, and having those traced through the rest of the software development life cycle. It is important that we have traceability, and I'll talk about this later in the class, but things do change a lot, and when things change, and if you have a good trace of of the artifacts that that requirement produces, it's easier to understand the impact of that change. So traceability is very important. You can do it manually. There's tools available to allow you to do that. Again, we're going to talk all about requirements tools later. Business rules, think of business rules as almost a higher level use case. The very broad business reasons for going off and doing something. For example, why does your business fundamentally exist? What are you trying to produce? And then the use case is kind of a level below that. So mainly these are the product features. I think, like I said last time, if you get the shrink wrap box and fries and you turn it over and read all the different things your application is supposed to provide, those are the product features, roughly. They define the function of the software, both in terms of input behavior and outputs. I've even seen requirement specifications written just like that format, where each functional requirement is essentially a template where the inputs are specified, the actual behavior, what the feature produces is specified, and then what outputs. It's a good template to use. It makes it very clear. For this particular feature, what do you expect to get in, and what do you actually produce? And each functional requirement of the system, you should understand those 3 points. If you have a good handle on the feature, you should be able to define all 3 of those things. There's different types of functional requirements, roughly 3 categories. There's calculations, algorithms, like a video processing algorithm for a video camera. So there's calculations. There could be just technical details and business rules. Think of IT systems. And then there's data manipulation and processing. Again, think of more of a database processing system where it's all about the manipulation of data. And when we get into modeling, we're going to talk about different views of software. Some of them are more event-based. For example, if you're designing a user interface, it's going to be very event-driven. If you're designing an IT system, it'll be very data-driven. And we're going to focus our modeling based on what type of system we're trying to design. But at the very highest level, think calculations, technical business rules or details, and then data manipulation. Okay, now, non-functional requirements, these are actually quite different. And again, the easiest way to think about the difference is functional is what the system shall provide. Non-functional is how well the system shall provide it. So it's a more global constraint. By global, there are some things that you can't measure from a non-functional requirements perspective until the whole system is put together. So for example, performance. You can't really measure performance of, say, a user interface until you have the software, the hardware, the operating system, the network, potentially, before you can actually measure. So it's a global requirement in that sense. I've got some examples coming up. That's why this next bullet cannot be implemented in a single software component. It's sometimes easier referred to as emergent requirements. You need the whole system to be there to really measure it. Now, you can measure performance of individual software components, but what you're getting measured on ultimately is what the system's going to do. Okay, think security. Okay, security, you can't measure it until you have really a system in place, because it involves hardware, software, and even the human to get a system requirement implemented. So that's why some of these things, it's very hard to measure it at the component level. That's different than hardware. In a hardware system, you can measure, for example, the reliability or the performance of individual hardware parts. It's a little bit easier to do, but for software components, it's a little bit more difficult, because reliability, for example, is measured differently in software. These things are hard to model. How do you model usability? How do you model performance? When we create use cases, which we'll do later on, use cases can't address things like performance, right? They can't address things like usability. There are ways of doing some modeling, but it requires a lot more work. For example, if you want to model scalability, which is a non-functional requirement, the scalability means, I'm just throwing out examples here, but most IT systems have you'll have relatively linear scalability. And then at some point, you're going to go like that. This is, think of this could be something like response time or something like that. So most systems, they operate linearly until they get overloaded. There's always a knee, and that knee, when you reach that knee, the system very quickly degrades. And so how do you know where that is, and how do you specify a requirement for how you want your system to be scalable? You can do this by these you can do by models and analysis. Okay, you can do some of this. Okay, to determine where that is, and so if someone tells you, I want your, HR system to support 1,000 users. Well, if your analysis shows that this starts happening at 500 users, then you've got a problem, right? So you can't just sign up for 500, 1,000 users without at least doing some analysis. So when I say they're hard to model, yeah, they are, but you can do some analysis. And actually, the requirements engineer is one of the guys responsible for doing this analysis. That's why, last week when I said the requirements engineer isn't the person that just talks to the customer and goes and tells the rest of the team. They sometimes have to get involved in doing some engineering work to understand where some of these performance issues are, like this one. So I'll get back to that later, but many of these non-functional requirements are harder to model and analyze. They're often stated very informally. Remember I told you about the example last time about the requirement that my USB interface had to be fast? That, many are stated informally like that. So, and often they can be contradictory too. What does it mean to be fast, for example, between two different stakeholders? Very difficult to enforce during development, and measure during development, and even evaluate for the customer prior to delivery. Now, I will tell you a couple techniques that have worked for me, but performance, for example, it's hard to actually deliver that incrementally. You can do some of it by optimizing, putting an optimization plan together, but usability is hard to evaluate prior to the customer seeing it. So one thing we can do to address usability as a requirement is get prototypes out to the customer for them to analyze. We're doing some agile projects at work, and we literally give our customer an update to the interface every month so they can evaluate it, give us feedback, evaluate it, give us feedback. That's one way of addressing some of these harder requirements like usability. But it does take a concerted effort to do that. A standard waterfall approach won't work. And it's hard to make them measurable. Measurable means putting a quantitative number on these non-functional requirements. One of the best ways of validating a requirement, okay, is to think of a test case for that requirement. One of the most effective ways of actually knowing whether your requirement is vague or not is literally write down how you would test it and know whether it passed. If you can't think of that, how you would do that, then the requirement is probably vague in some sort. So if someone says the system has to be usable, that's not quantitative, right? How do you measure that? Well, there are ways of measuring it. You can do a survey on a prototype. You can do prototypes. There's actually ways you can do it. But if someone just says they give you a requirement for a certain interface to be usable, that's a cause for concern. You want to go back and get quantitative. So basically, every non-functional requirement that we're going to talk about, you have to have a number, a quantitative number, to represent this accurately. Okay, almost every one of them. And we'll go through some of them later. So here, a lot of categories here. Lots of ilities at the top: understandability, usability. I'll let you can read through all those, but look at just all the ilities, and a lot of these are becoming more and more important with products today. And many of these are orthogonal. You can't get all these at the same time, right? For example, if you want something to be maintainable, you also can't get good performance because maintainability fundamentally drives an architecture in a certain direction, whereas performance drives an architecture in a different direction. I'll talk about some of these examples for you. So ilities, and then the ities, like security, simplicity, integrity, ubiquity, modularity, things like this. And then other categories, the .NES, okay, like user friendliness, we talked about that already. And then many other things like performance, which is a real key one now these days. For a cell phone, efficiency, memory usage, memory efficiency is a real big one. Anytime I could tell my customer I can squeeze their applications in a few megabytes less than my competitor because my compiler is more optimized, then the customer can put a few more applications or features on their cell phone. So efficiency, power is becoming really, really important. If your battery can last a little bit longer. And there are ways of optimizing for power using software optimization techniques. So these are all non-functional categories, and there's a lot of these that customers want. Okay, now again, eventually, you're going to have to pick which ones are important because not all apply. But for every one of these, if you just think through every one of these, if you had to test whether you met this, how would you do it? Each one of these has to have a number. Pick any one of them, and there'll be a number you can apply to it. Scalability. Well, how many users specifically do you want to scale to? It can't be infinite. Your database can't keep growing forever without something, bad happening. So every one of these, security, how this is referred to as a shall not requirement. Security, how long would it take for an average hacker to break into your system? You've got to, you have to state it like, well, it's got to take at least 5 hours. Okay, you've got to have a number there for every one of these. So we'll go into some of these categories more, but just keep that in mind. So two main classifications then, these all fall under what are called execution qualities, things that you can actually observe at runtime, like security or usability, and then evolution. These are things that aren't quite as obvious, but are very important, like maintainability and scalability. When I was in the defense business, maintainability was a real key one because the way they do their work is the people that build the system are normally not the ones that maintain the system. The people that build it, I was at Raytheon at the time, they have a contract to build it, and then the customer will usually go off and have a separate contract to maintain it. Now what that means is they want that software to be really maintainable so that if they give a contract to somebody else, they're not looking at a bunch of spaghetti code and assembly language and have no idea what's going on. Okay? So if I were to give you a maintainability requirement, what specifically would you do to achieve maintainability? Can you think of any ideas of what requirements would fall under that category of maintainability? Any specific things you would do?
Readable code.
Okay, readable code, which means, okay, easy to read. Okay, that's good. Well, what does that mean? Go a little bit deeper. Comment, so well-commented code. Module, so there's this, so modular code. Have you heard of this term called cyclomatic complexity? Anybody take testing, software testing? Cyclomatic complexity is a measure of how complex a piece of code is. It's a measure of all the if-then else's in there, and reducing that, essentially breaking it up into little pieces, makes it more maintainable. Okay, what else? What else would make code more maintainable? So readable. Sorry? Yeah, code complexity, that's a cyclomatic complexity. Yep, so definitely, so lowering the cycle. So you can have a requirement like the one I had was cyclomatic complexity had to be 20 or below for every component. Just to let you know how bad some of the software I saw recently, cyclomatic complexity was over 1,000. When you see cyclomatic complexity over 1,000, that basically means you have one file of 10,000 lines long of just complex logic. That's very, very difficult to test, maintain, fix it. Okay. Anything else? How about this one? What do you think is easier to maintain, Java or assembly language? Java, right? So you see requirements a lot that says you can't have more than a certain percentage of assembly language in your software. Again, that's for maintainability, things like this. Well-structured code. There's actually, there's this whole, concept of structured design where, you don't have, well, I'm aging myself, you don't have like go-tos or the equivalent of a go-to. So there's definitely this concept of spaghetti code where you're jumping all over the place, or just well-structured code. So okay, things like this. So under maintainability, which isn't an obvious, non-functional requirement, but one that could be very, very important to some customers, when you dive into that, you have to measure, everything. You have to have these quantitative. So you may have things like no more than 10% assembly language. You have to have at least n number of comments per 100 lines of code, et cetera, et cetera, et cetera. Okay? Cyclomatic complexity less than 20. See how every one of those has a number in it? That's what you have to do. You have to get to that level to be, for this thing to be truly, testable. So again, we have these execution qualities that are more obvious, the evolution, which are not, but still very, very important. These are the two general categories for NFR, non-functional requirements. Now, under there, you can look at how these things actually apply to process considerations. So they may drive your development method. We just got through talking about some of this, how you actually write your code. The implementation environment, tracing certain decisions, and then design choices. Let me give you one example of a design choice that, just to give you a, so if you have, let's pick one, which one should I pick? Let's pick safety. Maybe we'll do two of them. So safety. So here's an example of a design choice that you would make if you have a safety requirement. Okay, maybe you're designing a pacemaker, embedded pacemaker or defibrillator, and safety was a key concern. Let's say you have, this is your safety critical hardware. This is your pacemaker. Well, one architecture could be this component 1, component 2. You could have several software components that interface with that hardware, and your argument might be, well, I've nice modularized software components, low coupling between those software components. Coupling is a design decision. Low coupling, high cohesion. And so you can design it that way. Okay. Now, however, the FDA for medical devices has they impose higher regulation on any software that's actually going to touch safety critical hardware, like this pacemaker hardware. So anytime you have software that's touching this hardware, they set a very high bar on how you have to test it, evaluate it, things like this. So an alternative design choice, again, might be if this is your same hardware, and if I have my same components, let's say I have my same components like this. Now, rather than all of them interfacing with the hardware and you having to have this high bar for all these software components that interface with the hardware, now you're going to have maybe one, and then you might have your other modules go through C2 to touch the hardware. Now you only have one area that you have to, kind of go through these extra steps for, okay? That's one example, okay, of how a design choice, if you go back to the laptop, those design choices at the bottom left, some of these design choices could be made based on these non-functional requirements. See what I'm saying? That's one example. There's a few others that we'll get to. In the middle, there are a lot of product considerations. So we talked about many of these, like performance, capacity, et cetera. Integration is also important. Integration is essentially how you put together the pieces. One thing that may support integration is having, it may drive a requirement on a certain API, application programming interface, or set of APIs that are needed to help with integration. And then on the right, external considerations, and again, we have a lot of other issues, social, economic, even contractual, that will come into play here as well. So a lot of influences on these non-functional requirements. I've got a couple slides here that just allows you to maybe help memorize all these different types of non-functional requirements, because there's a lot of them. Here's one of them, Scruple. This is one that's been around for a long time, but the acronym, if you just read down through it, it'll point you in the right direction on some of at least the categories of these non-functional requirements. This is mainly just to help you memorize some of the categories we've already discussed. FERPS is another one. This one's used by IBM. FERPS, so functionality, usability, reliability, performance, and supportability. And you can see how they're categories for a lot of different types of non-functional requirement. But whatever, if you're into memorizing acronyms, this one can help as well. And then McCall, this guy came out of the Air Force. McCall has you find almost every standard out there has a set of non-functional requirements. McCall out of the Air Force, a different way of looking at the picture. Same thing, product, transition, operation, revision, and they've got their non-functional requirements mapped into these different phases, which I kind of like. For example, product transition. When you transition a product, it's about portability, reusability, interoperability. Like, for example, if you're transitioning a new hotel reservation system, that may be a requirement that interoperate with multiple different financial systems. Just to give you a quick example of how that goes wrong, I was project managing in a consulting firm, and we got called up to New York to talk about this. It was in the early days of creating exchanges. So you're familiar with the New York Stock Exchange. It's a central place to come and do business. Well, this was going to be an exchange for groceries. So big grocery stores putting all their products into an exchange, and so the mom and pops could get low pricing and this and that. But the limitation was the company that I was consulting with at the time. They only supported a couple different financial systems. Some of these lower end, relatively inexpensive financial systems. So I got sent to talk to a company in San Diego that was interested in participating in this exchange, and they were using an Oracle database. And now those things are pretty expensive, to get those things up and running and installed, and we didn't support it, and they were not willing to cut over to a new financial system just to participate in this exchange. That product that I was trying to sell didn't have the requirement of interoperability that was necessary to make that product successful, and that ended up not doing that well. So interoperability can be really, really important when you're designing systems. You don't want to put something out there that just doesn't work with all the existing infrastructure that's out there already. And then operation, we've already talked a lot about that already. And then, of course, revision, where you have the maintainability, the flexibility, and even testability. Software can be harder or easier to test. What are examples of making, what might be a requirement on testability? What would make software more testable? Well, what if I was able to provide you or the tester access to some of the internal data structures so that I can, test it and find out what's going on, things like this. So certain accessors into data structures as opposed to making everything private would make software more or less testable. Does that make sense? Okay. All right, let's move on. So defining non-functional requirements, here's kind of how you do them. First of all, you can treat these incrementally. In other words, you can break these up into different, for example, lower level requirements and build them up over time. Agile will support this, for example. A lot of these are cumulative, and so what you would do, again, here's what I said just earlier. Functional is the software shall do something. Non-functional, the software shall be something: fast, reliable, scalable, all the things we've talked about. That's the key difference that you need to remember. But let's go over here and talk about exactly what you should do. So anytime you're given a non-functional requirement, how should you actually go about writing it and describing it? So here's the generic template up here. You have to discuss a system dimension. In other words, the context. What is it you're actually trying to measure? Now, in my line of work, I build networking software. So I put an example of an actual project that I'm working on down here. So in the system dimension, the what, I've got a requirement today that I have to be able to do an algorithm called IP forwarding at a certain rate. IP forwarding is just, think of packets on the internet coming into a router, and the router has to be able to determine where it's going to go next and then forward those packets onto its next destination. Okay? Does that make sense? So IP forwarding, just essentially, it's the algorithm that does that. A little bit more difficult than that, but that's fundamentally what's going on. Now, the next thing you have to describe is an attribute. So what shall that dimension be? Well, in the case of IP forwarding, it doesn't have to be reliable. Well, I'm not looking for reliability. I'm not looking for security. I'm looking for speed. It has to be fast. So this particular algorithm, it can be many things, but I'm going to measure how fast it is. Okay? The next thing is I have to define what exactly the metric is going to be. How am I going to measure it? What's the unit? So the way I'm measuring this particular IP forwarding algorithm is in kilopackets per second. So this is how many thousand TCP/IP packets per second can I process. So you have to be specific about it. And then how will I know whether I'm meeting it? And there's a couple different ways you can measure this. One is, what should it be? And what must it be at a minimum to be successful? So I'm shooting for something, but it's got to be at least this or I'm not going to be competitive, right? So down here, I was shooting for 600 kpps, but I had to get at least 550. Now, by putting that range in there, that just basically says, 600, I'll get there over time, but you know what? I can't have anything less than 550 or I'm not going to be successful in the market. That make sense? A lot of these performance requirements like this may take some time to optimize it over time, so you can start out with a minimal bar and then you can raise it over time. So that's an example of how you would classify non-functional requirements. I picked performance, but you can do this for every one of them. So use that template system dimension, attribute, the metric, and then the should and the must, and that would be a good way of defining a non-functional requirement. Okay, do this for every one of them. This is an actual case study. So my team, one of the big things my team builds is something called the software development kit, and this is actually real data that I took from a project that we ran. Now, let me explain what's going on here, because it'll give you a good realistic perspective on how you actually do this in the industry. See this red line? That's the goal. That's essentially the must-have. I've got to get there. Okay, now see how that red line, time goes from left to right. That red line, see how that kind of goes up, ratchets up over time? I'm making software releases periodically, and as I optimize this algorithm, this is the IP forwarding algorithm, I can raise the bar on how good I expect to be over time because I know I'm going to get better and better as I optimize my software. And so that's the goal. The blue line is the actual. That's what I actually measured. Now this thing is called, in industry, this is called a crawl chart. And the crawl chart measures over time how well you're doing on a certain measurement. In this case, it's performance. So I have time and performance. So early on, I wanted to be at 300. I'm going back a little ways. And I was at 200. So what did I spend a lot of my time doing in the first software release? Optimizing to try to get to that goal. And then, as you can see over time, I had some ebbs and flows, but I eventually got there. I like to annotate my crawl charts so that at every point, I know exactly what I did to get that certain capability. Now, this was done as an agile project. So I was able to make multiple software releases. The first version was more of an internal release. The second one went to the customer, and we were able to meet their initial performance goal. A third release, they expected higher performance. The next release, higher still. And then we did some quality and hardening in the last increment. So what this is showing is that you set a goal for where you need to be. That's the requirement. You can set a plan for how you're going to get there, especially if you're doing an agile project, because you're not going to get there immediately in some of these non-functional requirements. Reliability and others follow a similar path. But you map it out and plan it and measure it so you know. This is real life measurement, quantitative data. It's not me going back to the business unit and saying, yeah, I think it's fast enough now. We have to go to a formal review to show these measurements before they sign off that I met that requirement. So these crawl charts is a very common part of how I measure non-functional requirements. okay? All right, now there's another approach, and this one is actually interesting too, called language. And I like this one because it forces you even more so to think about your non-functional requirements. And again, it's a template, but if you see one of these on a homework or what have you, it's pretty easy because all you have to do is use this template and follow these definitions. But let's just quickly walk through what this is saying. So you get a non-functional requirement. First thing you want to do is describe what's called the gist, which is a short, very simple description of the concept. This is where you can actually say the system has to be, the user interface has to be usable, or you have to be able to, schedule the conferencing system faster than the existing system in the market. This could be a high-level statement. But then you have to identify the stakeholders. Who's this really for? Is it for an experienced user, a novice user? Describe the stakeholder. The scale of measure. I just showed you one that was in kilopackets per second. The process or the device you're going to use to measure it. So how am I going to measure it? When I measure those packets, kilopackets per second, I have a board. I stick Ethernet in one side, and I record packets going into memory, and that's essentially how I measure those numbers I showed you. What's the must level? What's the plan? And what's the stretch goal? Can I do better if I did a little bit more software optimization, if I had a little bit faster processor? So it's okay to even talk about a stretch goal. And then there's even a wish, a desirable level. And it may not be attainable, but it's a wish. This is your wish list, okay? Just like on Amazon, right? So I've got my plan. I'm going to shoot for this, but you know what? I really wish I can get here, because if I can get there, I can capture more market share, or I can what have you. So it's okay to put that, because that sets a future goal, okay? Don't make it completely unrealistic, but it's always good to talk about the past. What's the system currently doing? If you've got your goal set, where are you today? Or where have you been in the past? It's always good to know where you're coming from. What's the best known that you've seen anybody do as far as security or performance? It could be one of your competitors, right? But might as well put it down there. Okay, that's what we're going after. That's the target. We're going to go beat these guys. And then what's the trend, the historical range, or even an extrapolation of data that shows, like for example, let's say again you want to get, okay, I'll talk about memory size, okay, or memory usage. Well, memory density follows the same path as Moore's law, roughly. And so you can say, well, you know what, historically, memory density has doubled every 18 months, just like Moore's law, and therefore I can follow that trend and predict that I can be here in another 18 months, and those trends can be very useful. I worked on a project once where one of the requirements was I had to store a certain amount of data back in these days it was on a hard disk, and we couldn't meet the requirement with existing technology today. But what we did say was, you know what, this vendor we want to use, every couple of years they're coming out with a new product. It's been that way for the past 7 years. So I think in a year and a half when I need to buy this, I think it's going to have enough density for me. And we made the decision. We said okay to that requirement because we felt the technology would be there when we needed it. So trends are also useful when you're trying to determine whether to sign up for a certain requirement or not. So this is called language. Lots of stuff in this template, but it really makes you think about the requirement. Here's an example. The one at the top, the system must be easy to use. That's the one you would get yourself into trouble if you signed up for, because everyone's got a different opinion of what that means. Now, down below, I've added in a little bit more quantitative material, right? Place an order in under 10 minutes without assistance by at least 80% of test subjects, and then it tells you with no previous system experience. So it says that they're an amateur, or at least with no or little training. So, okay, a little bit more quantitative. But if I put it into a language, it really forces me down to the next level. So this thing's got to be learnable. So I'm focused on the ease of learning with this particular system, and you can read down through the rest of these tags in the language, the scale, the meter, how I'm going to measure it, and then the must, plan, wish, past, including the old system, And then other information here, I'm going to define exactly what a novice is. Because even saying a novice, what does that really mean? Well, they're saying it. It's a person with less than 6 months experience with web applications, no prior exposure to this particular website that they're going to use to go schedule this conferencing system or whatever, okay? So it's a lot more data, but it gets you to think more about the problem, okay? Notice all the quantitative information here. To get this is not just pulling numbers out of thin air. This is, again, where the requirements engineer has to go out and probably talk to a lot of people, do some research, find out what the competition's doing. This is why requirements engineering is more than just listening to what people are saying. I mean, it is that, but it's a lot more than that to actually get it right. There's also something I just want to point out real quick, something called the non-functional requirement graph, where you can set your non-functional requirements as goals. You want to get to a certain performance level, what have you. And then you also have your certain solution constraints. Remember how we talked about that already, the different constraints you have. Maybe you have only a certain size processor or memory or what have you. Operating system, you have to use a certain version of an operating system, but you put your constraints kind of there in the leaf nodes. And then what you can do is you could begin to map out a way of achieving a certain goal based on those constraints. So for example, let's go back to the system shall be easy to use. Using this requirements graph, that would be at the top node. Now, what would assist a system being easy to use? Well, it can be easy to read. No geek speak, that would make it easier to use, right? No technical jargon. It would assist if it was, support multiple languages. We'll talk later on about internationalization and localization, which is important too in a lot of systems today. A single command access to many common functions. So these things could assist that goal of the system being easy to use. So you can do some brainstorming and fill in different options there. Now you can provide, so these are some ways that you could assist the system being easy to use. How about the screen? You can provide a screen that would assist. You can also provide a custom keypad, a QWERTY keyboard. Well, look at this. A QWERTY keyboard may actually impair single command access to common functions, wouldn't it? So you can actually begin to now say, well, that option's not a good one. You know what a QWERTY keyboard is, the typical keyboard you find in your computers. Well, a QWERTY keyboard, if that was what you provided for a command vector, then single command access, it kind of goes against that, right? You'd rather have a little push button or an icon or accelerator. So this would impair going in that direction. So for a single command, you'd rather use a custom keypad, right? For a screen, would you rather have an LCD or a plasma? Well, if you want it to be easy to read, LCD might be hard. So you can eliminate that choice, right? Looks like maybe plasma might be an easier choice. So this gets into looking at different options to solve a non-functional requirement and kind of going through a process of elimination, looking at different choices and determining which ones would help, which ones would hurt, understanding the constraints that might drive that, and the grayed out bubbles here are the choices that we would ultimately make. So if I had a custom keypad and a plasma screen, I believe I can support all of these key capabilities that would drive the system towards a more usable outcome, okay? Just another approach to kind of model in a more disciplined approach than, as opposed to just going in and trying to brainstorm without any real structure to it. So brainstorming is useful. We'll talk about that too. And you can do this, again, with every non-functional requirement. Now, we've talked about a lot of these. I've shown all kinds of abilities, right? There's a ton of them. And unfortunately, not only can you not get all these at the same time, some of them actually hurt other ones. So for example, this matrix, this relationship amongst these quality attributes, by the way, quality requirements is another synonym for, it's another way of saying non-functional. You'll see it different in different textbooks. But I have a non-complete, because there could be more of these, but I have some non-functional requirements across both axes, same ones. So that's why this diagonal is grayed out, because availability doesn't have any impact on availability. See where so we don't have to consider this. But every other one of these, we should rate how they would hurt or help other non-functional requirements. So for example, reliability, if I had reliability as a key non-functional requirement, well, that would also help availability. Okay? A system that's very reliable is also very available. Same with robustness. If it's very robust, it would also generally lead to high availability. And then there's some negatives. Flexibility and efficiency, a negative contributor. Why is that? Why is an efficient system not a flexible system? Efficiency meaning, think optimized for performance or memory. Why would an efficient system not be a flexible one? Go ahead.
It's always hard-coded kind of thing.
It's hard-coded, yeah. So yeah. If you want to get things very, very optimized, normally you're gonna do things like assembly language optimizations that are target-centric, that are very difficult to. Flexibility means almost like portability, very difficult to change it, move it around, things like this. So yeah, so if you want something to be really, really efficient, you're going to unfortunately be less flexible. And then look at this, also efficiency has negative contributions to interoperability, okay? Maintainability, because again, you may be writing, for example, more assembly code, so it's less maintainable. Less portable, we just talked about that. Less reliable. Why does that make systems less reliable? Well, normally when you optimize, do very aggressive optimizations, you tend to break stuff, right? I mean, it's easier to break stuff. More aggressive even compilers work this way too. If you turn on the highest level of compiler optimization, you've probably experienced at least one compiler bug. It tries to get very, very aggressive on how it optimizes, and sometimes it doesn't. It'll produce it's not supposed to, but it does. So okay, so you get the picture. So this matrix is a very good kind of decoder ring for looking at how you need to think about pairing up different non-functional requirements. So if somebody came to you and said, hey, you know what, your system has to be really, really fast, very, very optimized, and it has to interoperate or be maintainable with, with this new group I'm bringing in to maintain it, you'd probably say, let's talk about that. I don't think that's going to work too well, okay? So keep this as your little decoder ring. You don't have to memorize this, but it's a good little thing to have with you if you're ever in that situation. Again, efficiency tends to have a negative impact on almost anything, because anytime you optimize the system, you're really, you're putting it under a lot of stress. Okay, so those are some of the relationships. So summary here, you can't always get everything, and you got to be really careful, because it's like pushing on a balloon. You might get a little bit more of this, but a little bit less of that. So you got to be just careful on how you choose these things. Okay, so again, functional system shall do, non-functional system shall be fast, maintainable, etc. The shall is the operative word here when I talk more about writing requirements. Shall means the system shall do something. Should is more like a goal. Shall is you better do it, okay? And then when you're implementing these, because you always have to think a little bit ahead, even though it's said that, well, requirements is about the what, design is, not the how, and that's true. But if you look at some of the constraints I mentioned earlier, like operating system, if someone told you it has to work on this particular version of an operating system, or it has to be implemented in C or Java or whatever, it's kind of taking a little bit into the design aspects of the system. And so you have to at least think about it. You can't completely ignore it. And when you're designing your functional requirements, it is about, you have to think about the system design. Like for example, we talked about this, right? You have certain types of coupling for that safety critical example I showed you, or go in a different direction. And then the non-functional requirements drive even more architecture decisions. One of the things about non-functional requirements like performance, and this is a big mistake that many people make, is they believe that performance can be addressed after the product is built, and all I have to do is optimize the code. That's a huge mistake. Most performance is dealt with at the architecture level, how you architect the system. If you don't architect it properly, you're going to end up with huge performance inefficiencies or security. Like you can't test security into a system at the end. You can't test reliability into a system. You can't test performance into a system. All these things have to be done during architecture. Don't let anybody tell you different. It's hard to shoehorn all this stuff. Quality. Another thing people often confuse. You can't test quality into a system. You've got to architect it in. So non-functional requirements, really, your architects are going to be the ones that are really interested in your non-functional requirements. And so if you're going to give your non-functional requirements ultimately to an architect, you should have some discussion to make sure they understand what you mean by these non-functional requirements. Same with the design team on the functional side. Very important. They are one of the stakeholders. When you hand off your document, we're going to write a requirements document. When you have your requirements document, it's going to go up to management, right? And a bunch of other stakeholders. But keep in mind, it's also going to go down to your engineers. Your architects, your designers. So it's not just for management to read and say, yeah, this looks, it's important stakeholder, but if these guys aren't happy or there's still ambiguity down here, there's a lot of iteration that has to happen before you actually hand it off. So the engineers should be involved in some of the reviews of your requirements document. Okay, now there's also other requirements that are a little bit more volatile. Let me talk through a couple categories of these two, because these are in the non-functional area, but they're special cases, and I want to talk a little bit about them. Mutable. A mutable requirement is something that changes because of changes in the environment while the system is operating. Can anybody think of an example of a requirement that might change based on the environment? Any ideas of? So changes to the environment in which the system is operating. So so how about something like a cellular base station? Okay, the environment it's operating in may be, let's say, a rural area. Okay, maybe at one point when I was living here in Allen, it was actually considered a rural area out in the middle of the boonies, and now it's kind of a I don't even recognize it. It's kind of this, Dallas is just subsumed Allen, Texas. So if someone put a base station out there of a certain capacity, now it might be different as far as the amount of not just phone calls but data that base station may have to process. So as changes in the environment may drive mutable requirements to that base station as far as capacity, for example, okay? So you have to understand what these, where a change in the environment may cause you to go back and change the system. That's one example. Another one might be the automobiles. As automobiles go into different environments, right now, for example, one of the biggest consumers of American automobiles is China. Huge growing middle class. It's actually causing changes to the requirements for automobiles as far as cost and quality and things like that. So these are requirements that change as the environment in which it operates changes over time, okay? Those are referred to as mutable requirements, okay? Emergent. Has anybody ever had to put together a bicycle? You know, put the tires on, put it all together. Has anybody had to do that? Has anybody ever had to put together anything, a toy for your kid or anything, a piece of furniture, right? So let's use a piece of furniture as an example. So if you take the pieces of furniture out, there's legs and arms and pieces. That you can't sit on that right out of the box, right? You can't take like one piece of wood and try to sit on it. You might, I guess you could, but it wouldn't work very well, right? Bicycle, the same way. You can't take a wheel and ride a bike. So what do you have to do? You have to kind of put it together, and only when it's together, you then get what you're trying to get to, right? A place to sit, a thing to ride. Emergent requirements are kind of like that. Emergent requirement is something that you can't really measure and define until the whole system is put together. And I alluded to this earlier, something like, you know, performance or even usability, you can't really measure until the whole thing is put together. Does that make sense? Because it includes, security is another one of these. It includes software, it includes hardware, and actually a security policy also includes people. One of the biggest violators of security is not, or you know, security leaks, is not people trying to hack in using complicated viruses. It's people that are like, you know, hacking, or you know, people in the IT group that are logging on with passwords and stuff like that. So anyway, an emergent property, you need the whole system there. How about consequential requirements? These are based on assumptions about how the system will be used. So when the system is put into use, some of these may be wrong. Any idea of what may be a consequential requirement? So normally you find consequential requirements to help you solve what are called wicked problems. A wicked problem is a problem that you don't necessarily know how to solve until you actually start getting into it. And I've got an example coming up. But you know, the most famous one is our space program, NASA. Back when we went into space, do you think we had the whole problem solved? You know, we knew exactly how to support human life in space and how to orbit and how to, you know, we actually made some assumptions, and we, you know, we had to go through several iterations before we actually figured out what the requirements were. Some of those were consequential requirements. We tried something. We thought, you know, space travel would operate a certain way. It didn't, and we had to go. We didn't find out about it until the system was kind of deployed, and that's actually why we deployed several different spacecraft to kind of find out these things early on. Okay, so that's a consequential requirement. Another example of this would be, you know how there's a lot of work going on with disaster prediction, like tsunami prediction systems, earthquake prediction systems, things like this. That's another case where we make assumptions about how that system will operate in the environment. Some of those assumptions are wrong. We learn, we go back and we fix it. That's okay too. Compatibility, it depends on other equipment or processes. Very, very important here. Compatibility is key, because a lot of the systems that you're going to build are going to have to interoperate with equipment, different processes, different financial systems. I keep bringing that one up. But almost always you're going to have to interact with different systems, other people's software, different APIs, things like this. So compatibility is a pretty common one. Let me focus just for a moment. I'm going to go through this pretty quickly, but on timing and performance, here's some helpful tips when someone asks you to go off and come up with performance requirements. I like this approach. I use this with my team. I'll throw it out to you, see if it sticks. I talk about this one because it's actually pretty important. Timing constraints. Response time is really, I find this everywhere. Sometimes your system has to operate within an environment that's always changing, so it has to be responsive to those changes in the environment. there's some very obvious cases like echo time for pressing a keyboard, but there's four basic categories of timing constraints which drive performance requirements. And let me draw a picture first, just so you know what I'm talking about. So basically, what I'm going to talk about is you have a system. That's your software system. And that software system is going to get stimuli, and it's going to produce responses. Okay? And what I'm trying to understand is, or what I'm trying to explain to you is, there's a relationship between when you get stuff in and when you have to put stuff out. And one good approach of working through and having a discussion on timing requirements is to talk about all the relationships between the inputs and the outputs. So let's go see what that means. The four different possible types are shown there. A relationship between getting something in, stimulus, and producing an output. There could be a timing constraint on producing two consecutive outputs. I'll show you examples of all this. Or responding to two different inputs. Or an output followed by a subsequent stimulus. So let's take a look at all four of these. Stimulus, response, I just showed you what those were. Okay. So take the first one, stimulus response. So this is a constraint. Remember I talked about constraints here. It's always useful to spend time on these. This basically says, I get a stimulus. I have to produce an output based on a certain constraint, okay? And there's two different approaches. There's what's called a maximum constraint. So here's an example. I wrote some requirements just to try to give you a feel for this. How about this one? Again, stimulus, I get something in, and then I put something out. A maximum constraint would go like this. System shall generate a dial tone within 15 seconds of a user taking the phone off the hook. So in other words, what's the stimulus? Phone off the hook. The response is dial tone. So this basically says, from that stimulus, I have 15 seconds to complete something, in this case, produce a dial tone, or the requirement fails, right? That's called a maximum constraint. But there's also minimum constraints. Let's look at the second one. The system shall arm the door no sooner than 1 minute after the alarm on button is pressed. So if you're in your house or apartment, you hit the alarm, and then you have a minute to get out of the house before it arms the alarm, right? So that's different than the first one, right? That doesn't say you have to do it within a certain amount of time. It says you have to wait at least a minute before you do it, right? See the difference? So we call that one a minimum constraint, okay? So again, all about, it's all about something coming in, and when do I put something out, okay? All right, let's look at the next one. Response. So this means two consecutive outputs that your software has to be responsible for. So it's a temporal, time-based relationship between two outputs into, let's say, the environment. So here's an example of a maximum constraint. So the system shall initiate this door closing operation within 20 seconds of locking the landing gear in place. So what's the first response? The landing gear. So think of a system that would output, the first output might be a signal to get the landing gear to retract, okay? And then within 20 seconds, it's got to send out another response for starting to close the door. So if you're in an airplane, right, you send out one response and the wheels start going up, and then 20 seconds later, you actually start the door closing, okay? Within 20 seconds. So I can't wait more than 20 seconds. I have to do it within 20 seconds, okay? And then the other one is again, it's a minimum constraint. I have to generate this launch missile command no sooner than 5 seconds after generating a start battery warm-up. So what's the first response? It's a command to start the battery warm-up. And then what do I have to do? I have to wait at least 5 seconds and then send another output or signal that does this launch missile thing. So again, it's you see the difference. One, I have to do it within a certain time. One, I have to wait before I do something, okay? Okay, next. stimulus, stimulus. So now I'm getting two inputs into my system. So here's an example of a maximum constraint. You're typing in your username and password. Have you ever typed in like your username and you waited too long to type in your password and the time's out? You have to go back. Okay, that's what that is. So the first input would be username or identification. Then you have to type your password in within 15 seconds or else it's going to cause you to do something, start again or whatever. Now, on the other hand, the minimum constraint, pilot must press the launch weapon button no sooner than the fire ready. So I have to, the pilot is providing these two inputs, fire ready and launch weapon into your software system. Again, two inputs, but I have to wait. He can't do that in less than 10 seconds. He's got to wait a certain amount of time, okay? Now, okay, one more. I'm going to go through the last one now. And then this is the last one, response stimulus. So I'm going to output something from my system and then wait for something to come into my system. So an example of this could be the user. I have to dial a complete phone number within 1 minute of hearing the dial tone. So that means I hear the dial tone, so that's my response. The system gives me that response. And if I don't put something into the system, which in this case is the complete phone number, within 1 minute, maybe I get that fast dial tone or something like that, right? And then finally, the minimum constraint, if I don't make a menu selection within 5 seconds after the menu display, I may have to try again or something like that. So again, a response, a menu display, the input, menu selection. See how that works? Does that make sense? So think of it that when you're looking at a software system, first of all, and I'll tell you why this is important in a second. It actually is important to requirements. So anytime someone starts talking about performance requirements, make it simple. Draw this little box. That's the software you're being asked to build. You've got stuff coming in. You've got stuff going out. There could be many things coming in, all kinds of stuff coming in and out. That's okay. These don't have to be in any particular order. But what you're trying to do is understand the relationships between the ins and the outs. And there's those 4 different possible combinations, right? And what I would do, if you go through each category separately and say, okay, let's look response stimulus. What possible response stimulus relationships exist in the system? Have that discussion. Once you exhaust that, go to the next one, stimulus, stimulus. Just kind of walk through all 4 of them. And you'll probably discover that there are some in there that you haven't really thought about, okay? Okay, now why is this important, okay, to requirements? First of all, you can see how requirements need to be written differently based on what kind of relationship exists, a maximum or minimum. By the way, a hint that you have a maximum constraint is when you see things like within. That's usually an indicator that it's a maximum constraint. Anytime you see things like no sooner than or stuff like that, it's a minimum constraint. Every one of these are kind of structured that way. Within, no sooner than, a very good hint that you've got one of these constraints, okay? Now, why are these important? Well, stimulus response and response response, the requirement is on performance optimization. It's how fast can the system do something, right? Remember, stimulus response, I get something in, I have to produce something out within a certain amount of time. That's all about how fast your software can do it. Same with response response, right? So the requirement, when you see those types of relationships, that means you have to think about making sure your software or your system is fast enough to get that job done. Now, how about the others? Stimulus, stimulus, or response stimulus. These are completely different. If you have one of these relationships, it's not about how fast your system is. You have to now, your system has to do something completely different. It has to monitor the environment and make sure that the environment follows the rules that are specified in these requirements. So for example, stimulus, stimulus. Remember the example there was type in your username and then password? And you had to do that within 15 seconds or you have to start over again, right? So what does the system have to do differently? The system now has to monitor the environment and probably start a timer, count down 15 seconds, make sure that the password is in, And if it isn't, it's got to go back and take some action, start all over again, output an error message, whatever you want it to do. So one requires optimization, the first category. This category means you have to add more software to detect the inappropriate stimuli, to generate the warnings and error messages. See how they're quite different? So if you understand these different categories like this and you go through this process of just kind of binning them out, it'll help you understand more about what exactly your software has to do to implement those, or to implement those requirements. In this case, again, these would be new requirements. These would be, obviously, you'd look for I'm sorry, this one you would actually look for a quantitative number to define what those relationships are, which, as you can see back here when I did this, you see every one of these has a number in it. See how each one of these has a number in it? That's to my point earlier. Every one of these non-functional requirements has to be measurable, quantitative. You have to be able to test to it. So that's why you see those in there like that. Okay, so that's on a little bit more on timing constraints. Okay. Any questions on that? These non-functional requirements, again, the summary would be they're hard. It takes some work to come up with quantitative, to make them not vague. The numbers don't just come out of thin air. You have to go off and actually, think about it, do some analysis, do some research. It's kind of hard. That's why, in my experience, I find the non-functional requirements almost always are the ones that are more poorly done, because it's hard. People don't like to do it. They like to tell you it's got to be fast, as opposed to it's got to, like I showed you earlier with that crawl chart and all the detail. So they, you as a requirements engineer, though, have to try to get very quantitative and specific. Okay, let's talk a little bit about safety critical requirements, because this is another category that kind of falls into this non-functional area, but it requires a little bit different approach. So by the way, your homework 1 is going to be on non-functional requirements if you had a chance to look at it. As a matter of fact, let's take a quick look at it now, just while it's fresh. So what I've asked you to do in homework 1, and again, all about non-functional. So I've asked you to, first of all, read this little description of the system. And what I want you to do is describe some of the non-functional requirements that should apply to this system. Okay, and not too difficult, but you saw all the different non-functional requirements. You may want to think through those. Which ones do you think would apply to this directly or even maybe indirectly? Next one, Robco. I couldn't think of a better name. Is gathering requirements for a software-controlled furnace. And so here, what I'm going to do is I've got this requirements list. It's only 4 of them. And I want you to go through these 4 requirements and just tell me which ones are ambiguous, design-dependent, incomplete, unverifiable, and explain. So there's some things in there that aren't quite up to par. Tell me what they are, why, what you do to fix those. Okay. Non-functional. Then I want you to go out and I want you to read a couple articles online that are in there. They apply to this discussion of non-functional requirements. So elections these days are actually getting, they're changing a lot, right? And I'm not going to get into a political discussion, but in the last political, when Obama came into office, one of the things he really took advantage of was what? Social media, right? I'm not saying that's what led him to win, but he certainly utilized social media to a very large extent, okay? And the guy running against him, Romney, also tried to use a lot of information technology to help promote the election. You're going to find more and more of this happening in upcoming elections, where people are finally starting to get how important social media is and things like this. However, there were some hiccups in some of the information technology that Romney was using, and it ended up causing a lot of problems with the volunteers that he had in place to go out and get the message out. And some would even argue that these software problems ruined the election. It was a fairly close election, and now who knows? But the fact that software was brought into the discussion on possibly, losing an election, I thought it would be interesting. I went out and looked at this, read some of the articles on this topic, and there's some non-functional aspects to this system that I've asked you to read, and I've got the links here. Both those links are take you to similar articles. They just give you different perspectives, and go read them. And based on what you're seeing, and you can do additional research if you want as well. There's other articles I think online. What would you think if you had to approach it from a purely non-functional? So again, go back to all those different non-functional requirements. Which ones you think were important? Which ones you think they could have done a better job at meeting when they were designing that system, and why? Explain your answer to me. It would be fun little research project. Just a few paragraphs, but explain to me, the problem and how you would have solved it. And then there's another interesting article here about why software fails. And there's more and more of this going on. And IEEE Spectrum has a really interesting article. I'm not logged in. Go read that as well. Why software fails. It'll give you another perspective on how, if you don't put the right emphasis on some of the non-functional requirements, it can quickly lead to failure. Functional, I'd almost say, is almost kind of easy. The key features, that's actually kind of easy. It's all the non-functional requirements that I believe can really doom a system. So go read those articles and comment on those, and then the others are just dealing with the non-functional discussion we just got through having, okay? Homework number 2, I think we'll talk about this next topic, so let's get into this one. So safety critical requirements. If you're building a pacemaker or a defibrillator, I've got some colleagues of mine that do this. They've run software departments that actually build the software that goes into defibrillators. Do you guys know what a defibrillator is? So you ever see those commercials? Like there's one on TV now where the guy has the panels and he says clear, and the guy he zaps the guy, right? Well, that's a defibrillator. You see them in airports and other places where people could have a sudden heart attack. Well, you can actually put that same technology inside of you. It's an implantable defibrillator, and these things detect certain abnormal heart conditions, and they'll literally kind of zap it back into normal operation. They're actually, it's great technology, but they have to operate safely all the time. You don't want these defibrillators, for example, shocking you because you're on a treadmill and your heart rate is up, and so it has to be very well tested and designed so that it only detects certain abnormal situations. So the FDA, the Food and Drug Administration, which manages these safety critical devices like medical devices, have requirements for how you build up the capability and how you specify the requirements for these types of devices. Same with aircraft and other safety critical systems. Otherwise, a lot of damage could happen. So there's many different types of safety critical systems. I talked about implantable devices, but there's many others that we all partake in. Automobiles are getting more and more that way, of course, planes and trains and all these other things. Now, there's a lot of safety standards out there. You don't have to know these, but just to let you know that many of these key industries have a standard that has to be followed. Some of them are defense-oriented. Some of them are ISO, International Standards Organization. This is another European standard. So there are all kinds of standards out there that have to be followed. But most of them require a certain approach to doing requirements, which is what we're going to talk about. So given those non-functional requirements I talked about earlier, which ones do you think might be useful for, it says here embedded systems, just think safety critical. Reliability, obviously, is one. Maintainability, these things have to be maintained and fixed and evolved. For example, here's an example of this. If you have a pacemaker inside of you, how would you reprogram it? If you want to download, you can actually download new software, new parameters into these pacemakers or defibrillators. How do you do that? You think the patient has a little JTAG connector sticking out of the side of their rib that you plug something into? How do they do it? Bluetooth? Telemetry. They have a little telemetry wand. Yeah. We program it with telemetry and a little programmer, a little laptop programmer. But so so these things do get loaded with new software, just like everything else. So maintainability has to be of key importance. Of course, availability, it's got to be available a lot, secure. I think I've got a slide in here, but if I don't, believe it or not, there was just a recent hackers conference that happened in San Jose. There's another. They actually have one big one that also is in Austin every year, and one famous hacker, I can't remember his name, he has now said that he can hack into pacemakers. So he is actually able, now he hasn't gone off and tried it on a real person, but he's evidently demonstrated that he can hack into these implantable medical devices. So what do you think that means to security? So these things are really big in areas like that. Keep in mind availability and reliability are not the same thing. I've got a little example of a home network system. If you drop every 100th packet and that causes a retry, to the user, it's still an available system, right? It's still working, it's available, but it may not be as reliable. See the difference? Sometimes these things can get mixed up a little bit. There's no periods of outage, even though you could question the reliability of the system because it's dropping packets. So similar, but you have to be very careful how we define these. I pulled these. This literally took me just a few minutes. There's so many cases about security challenges online. Here's the pacemaker one, okay? And that was a year ago. The guy, or 2 years ago, the guy has been traveling, promoting his ability to do that. This one here is interesting because it came out of Austin. Basically, a guy went into a car dealership in Austin, was evidently not happy with the service he got, or maybe the price he got. He was able to go back home and hack in. And in these car dealerships, you ever wonder when they go home at night if somebody just come along and get into one of these brand new cars and drive off in it, right? Even though they block the front, they're still, they actually have their IT systems actually can lock the car down so you can't start it. So within the dealership, you can actually, through their IT systems, they're connected to the cars, you can actually bring the cars into a state where you can't start them. Well, this guy hacked into that IT system and was able to prevent the dealers, when they got in the next day, from opening any of their cars or starting them. So all their cars were basically inoperable, so they couldn't give anybody test rides or anything like that. He hacked into the IT system in this car dealership. So these challenges are everywhere, and we have to be able to respond to them. Now, a lot of safety requirements come from different sources. One is by talking to the customer, what similar products have in the marketplace. The requirements engineer should be knowledgeable enough to go off and know that. Competitive intelligence, professional assistance from these standards bodies. And then once you have all that, you should have a good start at putting these things together. Now, when you're doing, actually I'm going to skip this one because this one isn't, I guess I put this in here because in all the steps you have to go through to eventually start the process of developing a safety certification, one of the biggest issues is failure to recognize safety requirements as real. So there's a formal process I'll walk you through to do that. This slide, I threw it in here. I'm not going to read through it. I'll let you do it. But this is basically just describing the difference between a fault and an error. and a failure. They're actually not all the same. I think I have a picture here. A fault may or may not. It could exist in your software. It could lead to an error if the user exercises that piece of code, and that error could lead to a failure. May or may not. It could lead to a failure. So all of these can impact the reliability of the system. So what we're trying to do is understand what could possibly happen here and how can we fix it back here. Okay. So one approach we're going to do that. Let me skip over these slides on these 4 aspects of fault handling. You're not going to have to remember this. I want to get to this hazard analysis. For safety critical systems, one thing that the FDA or most watchdog organizations will require that you do is a hazard analysis. Now, a hazard analysis is an approach whereby you look for potential hazards and you add software requirements to help you recover from certain or prevent certain hazards from occurring. Okay, let me give you a simple example, then we'll go into more details. Okay, if you're a patient in a hospital, okay, patient, and if that patient requires breathing assistance, they put a mask on, right? Put this mask on. Sometimes it goes to a big thing, big tube that they carry around to get their oxygen. But in a hospital room, these are actually this is not pure oxygen, right? We learned that way back in the NASA days. Pure oxygen is very flammable. So normally what do they do with oxygen to get it safer but also breathable? They mix it with nitrogen, right? A little bit. Now, there's a certain mixture. And normally this may go into a wall. And actually even a better case would be at a dentist when you're putting on your mask that nitrous oxide can. But anyway, whatever example you want to use. But anyway, there's a certain mixture. One thing you don't want to do is cross those up, right? So if you accidentally had a tube that was supposed to be for the nitrogen and you accidentally plugged it into the oxygen and vice versa, that would probably be a real bad thing, wouldn't it? Okay? So what requirement, what would you do to prevent that hazard from occurring? The hazard is that you could mix up these 2 tubes and it could lead to the patient potentially dying or breathing the wrong mixture. So what would you do? Would you solve this problem by maybe adding another requirement into this system? Any ideas? What can I do to prevent these things from being... Change the size? Yeah, yeah. Which is exactly what they do in hospitals. So the connector are different sizes, so you can't plug one into the other, right? So that was a requirement that gets added. But first what you do is you identify the hazard. And once you identify the hazards and what contributes to the hazards, you can go back and design requirements to help alleviate those hazards. In its essence, that's what we're trying to do with hazard and fault analysis, okay? Does that make sense? So let's just talk about a little bit of this. So a hazard can be any potential failure that causes damage. The damage could be physical, it could be economic. It doesn't have to necessarily be like loss of life, although that's obviously the key one, but it could also be economic damage and things like this. If a particular aspect of a system fails, you want to make sure it still operates in some safe state. Now, a safe state can vary. Okay, let's say let's consider I've got one of my colleagues works for General Electric trains. Software controls a lot of trains on tracks these days. So if something went wrong with that train, what might be a fail-safe state to put that, to send that train into? What would you do to that train to kind of make it safe, you'd probably shut the engine off, right? It's on tracks, it's going pretty fast. If something was detected that ends up being a hazard that could cause damage, that might be a good state to put the system into, right? I mean, after all, it can't cause much harm if it's just sitting on the tracks. Okay, would you, now let's say you're flying in an aircraft at 33,000 feet and something happens. Would you do the same thing you did in the locomotive and turn the engines off? Probably not, right? You'd probably do something completely different. So the fail-safe state is going to vary based on what you're trying to do, or the type of system, okay? So what we have to do is go through this analysis and probably start by identifying all the potential hazards and then working our way up, which is kind of what we're trying to do here. So these failure mode definitions can be fail-safe. For example, the requirement would be there's no attempt to execute the operational mission anymore. In other words, maybe you stop the system, stop the train. You can fail operational, where you try to correct the fault and continue with the operational mission. So an example of this is like if the nav system fails in an aircraft, you don't shut the aircraft down. What do? You switch to a backup nav system and continue the mission. Okay, so you continue the operational mission, correct or work around it, and then fail soft is where you continue with degraded operations. So if you had in a network, for example, if you had a failure, what could you do? You can route around the failure, maybe operate in a degraded mode, but you're still operating, right? Which is how our bodies operate. When you get cold, what gets cold first? Your extremities, right? Fingers, toes, right? Why is that? What your body's doing is it's protecting the most important things. Your organs, you're in right here. It'll sacrifice these guys to keep this warm, which is, you can live without your hands. You can't live without. So it kind of takes a fail-soft approach. It'll allow you to continue with degraded operations. Does that make sense? So it's a similar approach with engineering. So we'll continue. A lot of safety critical systems will keep important tasks running and starve other tasks that aren't important just to keep the system doing basic stuff that'll keep it alive. So deciding which one of these ultimately has to be fed into a requirements document. So a hazard analysis, what you do is you look for potential failures. So in this particular example, I'm using an example of a vehicle speed sensor. Okay. Now, sensors, and this actually is what's done on a lot of vehicles today. And as we get into more autonomous driving, you've seen Google do some of this already, and other companies are also starting to get into this. Sensors are going to be very important to help manage these autonomous vehicles. You see some automobiles today coming out with some of the stuff like the backup detection and automatically puts the brakes, all that stuff. But it's going to get much more than that in the next decade or two. So these sensors could fail. Now, if this sensor fails high, it goes out of range high, what are the potential effects of that failure? The cruise control could go off from on, potentially, or maybe the other way around, but usually off from on. Is it severe? Well, you're going to have to apply some consistent scaling to that. Normally a severity rating it can go from 1 to 5 or 1 to 10, depending on which approach you use. But you want to be consistent. Actually, the number itself isn't that important as long as you're consistent about how you apply it. What could be the potential cause of this failure? A short, okay, a high side short. The occurrence, how likely is it to occur? Low occurrence, relatively. What's your mitigation plan? Add overload to the sensor connection. In this particular case, you would add a more robust sensor connection. What's the detection rating, meaning how easy is it to detect? And then this thing called the RPM, risk priority number, is just you multiply 5 times 2 times 3, you get 30. And you ultimately will prioritize all your risks this way. So in software, I'll show you some software ones as well. What you would do is you would look for all kinds of potential failures in the system, like locomotive, aircraft, baggage handling systems, whatever. And what can you do, what would be the mitigation plan in software to try to overcome one of these failures? Oftentimes, this hazard analysis, you can end up with hundreds of these things. And how do you do it? Well, the way you actually would put one of these together is you would, the way it works in kind of in real life is you get some domain experts, the ones that really understand the system, the hardware, systems engineers. Sometimes you even need more specialized domain experts that understand certain components that can tell you how certain things might fail. The requirements engineer is not going to know all this themselves, so it's a team of people. And you'll go through multiple meetings to try to get this data. But once you have all the data, you have to rank them. The risk priority number is one way of doing it. But then what you have to have a discussion on is how can you, what's the mitigation plan? How do you actually get around some of these? Some might be hardware fixes, some might be redundant nav systems, which is kind of hardware and software. Some might be purely software. It could be as simple as if you get it out of range, the solution might be read multiple times. Maybe the first time was just an E&M pulse or failure, so the response might, or the mitigation plan might just be to check multiple times. So it all depends on what you're trying to accomplish. But this template, keep this template. We may use this again in the future. The functions, the failures could be, again, if anything, I'll give you some of what these would be. It could be a certain hardware or software failure, and you'd have to tell me what you would do to try to mitigate that failure. Drop packets in a network. Well, maybe you want to retry. Maybe you want to switch a network connection, things like this. I'll give you some guidance on this, but that's the template you would use to try to put together a game plan for how you would mitigate it. Okay. Now, how do you come up with the severity rating? Some of this is by discussion over what damage would be the largest if the particular failure occurred. And so that's somewhat subjective. The whole risk priority number is somewhat subjective, but as long as you're consistent in how you apply it, it's still a useful indicator. Let's look at one more thing that I think you'll see this on your homework. I think it's homework number 2. It's a fault tree analysis, and this is one way of going through and adding a little bit more formality to the way you would understand the root causes of potential faults in your system. So, has anybody seen one of these before? A little bit? Okay. They're pretty simple. The way these work is you start off by having a discussion of what could go wrong, what potential faults could occur in your system. The fault could be an interface breaking, a nav system malfunctioning, a pacemaker, oscillator, clocking. If your pacemaker, clock, or oscillator suddenly breaks and it's all of a sudden now twice the frequency, that could cause a problem. So you look at all these potential failures in your system and you ask yourself, okay, what could cause that, and what could potentially cause these faults to occur? So you put the fault in the top, unintended acceleration in, let's say, what's it? The automated driver systems in cars. That's the fault, and then the tree is looking at the fundamental elements that could lead to this. So in this particular example, what could cause an unintended acceleration? You kind of back up. Well, the braking system could fail, or the throttle system could fail. If either one of these, this is just a simple OR. Most of the fault trees that we'll be doing in this class will either be an OR gate or an AND gate. I think you all know what those are, right? So if either one of these occurred, you'll get this fault. Or you can have it as an AND gate, which meant both have to occur to get this fault. Okay, I should have put an example in here with OR gates and AND gates. But anyway, so if either one of these occurred, we'd get unintended acceleration. And then you back up again. Well, what could cause the braking system to fail? Well, in this case, I can get a pedal actuator out of range or a brake pedal switch fail. If either one of those occur, this would occur. and if this occurs, this would occur. So you can kind of work your way up. And I'll go show you the homework in a second, which is a little bit more software-centric. Same thing on the throttle system, but the idea is, based on the potential fault, you want to back up and look at the fundamental contributors that could lead to that fault. And once you identify those fundamental contributors, you can then go look at how you can potentially solve those or work around those or alleviate those from happening, okay? So first you have to understand the fault, then you kind of back up and understand what could lead to that fault occurring, and then find a way of fixing it, okay? Why do we do these? Because these effects can have a very big impact on people's lives, financial, et cetera. It's also done to gain a really good understanding of the system. What I found is by getting a bunch of stakeholders in a room and literally going and brainstorming on what could make the system fail, you actually learn a lot about the system. You can document the failure relationships. This is what is required for safety critical systems. And down here, these will also feed into the requirements document. So ultimately what you decide to do to help alleviate some of these effects, you're going to actually add those into the requirements document, which I'll show you coming up how that's done. This I'm not going to discuss. This is a risk of entry analysis. I'm not going to talk about this. It allows you to apply probabilities to certain failure events. You can read through it, but I'm not going to talk about it right now. This is the process that normally gets followed. So you go through a hazard identification phase, document those, do the risk analysis. This will help you decide which ones you want to classify as important. Your risk assessment should get documented out of that. You decompose your hazard into a fault tree, like I just showed you. And once you decide how you're going to solve or alleviate those potential faults, the risk reduction, those feed into the safety requirements. So basically, your hazards, okay, which you can categorize using a fault tree analysis, ultimately lead to additional safety requirements. So when you have a safety critical system, when you show the FDA or the government agency your requirements document, they are going to expect to see this entire process followed. If you can't document your hazard analysis, your fault tree analysis, and how those feed into this document, you'll never get approval to build that product. So it's required that you go through this process and show the artifacts that you've actually done it. So that's kind of why I want to walk you through it, is because with safety, it's not as ad hoc as just coming up with numbers and doing some analysis. You've got to go through a much more disciplined approach for safety critical requirements. Okay. All right. Now, let me just. This is the last section I'll talk about. Then I'll quickly show you homework number 2 if you want to get started on that, and then I want to spend a few minutes talking about the project. So let's just go through this 8 steps of safety. This is a very practical approach that I've used. I think most of the industry follows this. So let's just quickly go through this and then we'll stop. So 8 steps of safety. Safety analysis, if you hear safety analysis in the industry, it's about the identification of hazards, the risks associated with those, and then what are the safety measures we're going to take. Now, a lot of this is handled at the architectural level and the mechanistic level. So this is handled at the systems level. Eventually, we'll create good requirements and designs and implement that, et cetera. But it all starts with the safety analysis. So let's talk about that first. So again, hazard analysis, when you're looking at identifying the hazards of the system, remember how I said you have to kind of form a team, or well, you do. Design, management, maintenance. There's a lot of people that get involved in that effort to help identify which hazards are important. And as I said earlier, this is ultimately going to feed into the requirement specification. So you have a lot of, even the test guys and the quality assurance guys have to be part of that team that's involved in that effort. Normally it'll be led by some domain experts, but you need these other stakeholders involved as well. So identifying the hazards, this is going into a little bit more detail. I'm going to throw out some ideas for you. So if you're confronted with a safety critical problem, like maybe on your homework or maybe on an exam, you can use this. Or if I'm not sure if I've got a project that has some safety critical aspects to it. I think I do with the autonomous vehicle project. You can even use this to help you with that. So the first thing is you have to identify the hazard causes. What causes hazards? Well, generally it could be a number of different categories, but here's some examples. Anything that releases energy. Now remember, even though we're talking about building software, you have to understand some of this stuff. For example, even in a simple microwave oven that releases energy, electromagnetism, there's some safety things built in, right? Like for example, if you open the door, it stops. Pretty, not saying software controls all that, but software is involved in a lot of those safety. Software is certainly involved in a lot of nuclear power plant where radiation is concerned. Electricity, heat, kinetic, all these things are release of energy. All these have hazards associated with them, and software can contribute to helping with these. Release of toxins, interference with life support, like think of a piece of medical equipment that's keeping somebody alive, like that little breathing example I went through. Misleading safety personnel. What if your user interface tells the safety personnel to go do something that's the wrong thing to do, right? So we have to, user interfaces come into play here. Or just failure to alarm. I'm not sure if you guys have heard about the Therac 25. It was a radiation machine that killed a number of people because of various software and other hardware issues. But one of the problems was it kept alarming the user so often that things were going wrong when there really weren't things going wrong, that the user eventually started to ignore the alerts, including the ones that were important. It's a big case study. We'll talk about it if we have time later on. So failure to alarm. All these are hazard causes that you have to be aware of when you're designing a system and how these could potentially lead to damage. Let me just build this up. So here's a whole bunch of actions based on these hazards that we need to be able to consider. For example, hazards include actions. There's a famous example, and there's a picture somewhere on the internet of a pilot, I think it was a pilot in Russia, that pulled up the landing gear of a fighter jet while it was sitting on the runway, and the landing gear came up. And so the jet, it wasn't in the air, it just crumpled right on the runway. Don't you think that weight on wheels, which is a sensor that tells you that the aircraft is on the ground, would have prevented the landing gear from coming up when it was on the ground? Okay, that didn't happen, right onto the ground. Or appropriate system actions, so that's an inappropriate action taken, or an inappropriate action not taken, or appropriate action not taken. Can also, that's why you have pre-flight checklists with aircraft. Timing of something, too soon, too late, fault latency time, too much or too little. Different sequencing or skipping actions or actions out of order. Actually, this is the perfect example of a pre-flight checklist. Pilots get very confident after you fly 5,000 or 10,000 hours in the air. They tend to skip steps. That sometimes can cause problems. Most of the aircraft accidents are because of pilot error, human error. Having a sequence that you must follow, not allowing them to skip actions. They experimented for a while with a user interface in the cockpit, and instead of a manual checklist, they actually had user interface checklists, and if the pilot didn't specifically check off things, it wouldn't allow the aircraft to take off. It's not fully deployed, but they're experimenting with things like this. Doing too much of or too little of something, actions, timing, sequence, amount. So you can look at these. I've got some examples here of what happens when you don't do these things, what could happen. Okay? Okay, so how do I control these hazards? Well, there's a long list of things you can do. And, obviation. Oops, let me go back. Okay. Can you remove the hazard by making it physically impossible to do something? Remember the fasteners we talked about? Make it physically impossible to plug oxygen and nitrogen into the wrong thing. That's referred to as obviation. You can educate, you can alarm, you can provide interlocks so that it prevents you from doing something. You can do internal checks, add more safety equipment, restrict access, and even simple things like labeling. So there's a lot of hazard control actions that you can do. Each one of these, by the way, would lead to a new requirement. So once you identify it, so basically the approach would be once you identify these different hazard types, you then would say, okay, how would I control these hazards from occurring? And if you picked anything in this list, it would essentially go into your requirements document as a new requirement. Does that make sense? Okay. That's the approach you take. I know I'm going through this pretty quickly, but I don't need to read all this. I'll let you read it. But that's the approach you want to take to do this kind of hazard control. You have to understand the risks. For each of these hazards, you have to understand the potential severity, that little table I showed you, the likelihood, even how long the user may be exposed to a hazard. Sometimes it's okay to expose them for a while, sometimes it's not. And then can the risk ultimately be removed? And so there's an organization called Tough TUV. It actually produces a risk determination chart like this, and it'll do this for everything from automobiles to children's toys, everything. What you do is you take the product, the car, toy, and you go through this risk determination. You look at the extent of the damage if the particular risk occurs, like one of those hazards. Anywhere from, if it's only a slight injury, like the toy might, harm a baby but not, kill it. S1, all the way up to catastrophic consequences with several people dying, like maybe a plane crash. You pick the extent of the damage if that risk occurred. The exposure time, how long can you expose someone to that? Seldom to relatively infrequent or frequent to continuous. So how long or how often would someone be exposed to this thing happening? How often would a person driving a car be exposed to a shrill noise because of a bad braking system or something like that? So exposure time. The hazard prevention. Can you do this under certain circumstances, or it's hardly possible to do it at all? So can you prevent it? And then what's the occurrence probability from very low to very high? If you trace through this, you'll ultimately end up with a category. Now the W is just these W columns here, and then the S, the E, and the G are just tracing, you pick which of these risk parameters and which level. And these arrows are going to take you to some number. So for example, if the extent of damage is catastrophic consequences or several deaths, you don't go through any other decision. You go right to level 8, which is your highest risk level. At the highest risk level, you may be asked to do a certain set of requirements to alleviate that risk. If you end up down at the lower levels, you know what, maybe this is where you just say caution, right? As opposed to prevention. Does that make sense? This one down here, you might say something that's a low priority level, you might just say, hey, watch out for this happening. Over here, it's like software's involved in shutting something down so that the radiation doesn't kill you, okay? So you map your way into one of these levels, and at each of these levels, you make a certain decision as to, or you will be told by this agency what you have to do to alleviate these risks. And this will drive new requirements into your requirements document. You'll determine those safety measures. Those safety measures could involve removing the hazard or reducing the risk of that happening, or it says here, identify the hazard to supervisory control. Basically what that means is punt it to somebody else. Okay, now let somebody else deal with it. Okay, I'm not going to deal with this. Sometimes this is valid. Instead of saying, you know what, I can deal with it here, sometimes you may have to say, I can't do this, I have to have somebody else take care of this. That's valid too. Then you have to make sure you go to supervisory control and tell them, hey, you have to deal with this, not me. Okay. So those are the measures you take. I'm going to skip this one. We're not going to have to worry about this. You have to reduce the risk, identify the fault, take corrective action. There's a couple different ways of doing that. Redundancy, like a redundant nav system. With communication systems, there's Hamming codes that can correct these faults. You can redo, okay? On these embedded pacemakers, you know what they do? Every single time they read a piece of data from memory, they actually read it twice and compare. And if that comparison doesn't compare, there's an issue. So every single thing they read, they do it twice. And then they compare. For those safety critical systems like a pacemaker, that's necessary. Or again, you go to a fail-safe state because you can't fix it. Sometimes you can roll back, try again. Okay, fault identification at runtime. Sometimes faults, you can identify them before they happen. Sometimes you can't determine them until after they happen. If somebody's doing a denial of service attack on a web server, it's impossible to prevent it. So you can't necessarily prevent a denial of service attack, but what can you do instead? You can find out when one's happening and then minimize the damage, right? You can download code off the web that'll do a denial of service attack for you pretty easily. It's very easy to do. It's all about detecting when it's happening and taking steps. So there's different approaches to that. Okay, so redundancy, I think this will be my final, actually, a couple more slides and we'll be done. A couple different ways of dealing with this as well. Redundancy is a big one. You can have homogeneous or heterogeneous approaches to redundancy. Homogeneous is like the space shuttle. 8 nav systems are all the exact same system running the exact same software. If one fails, they just swap to another one. The advantages of that, it's pretty easy to do. You cookie cutter, the same software, same system, easy to produce multiple copies. The downside is if you have a systemic problem in one, so for example, if the software has a bug, they're all going to fail the same way, right? With heterogeneous, you can maybe look at having the same redundant system but produced by multiple different independent teams. It's a lot more costly to do that, but you end up with systems that may not fail the same way because they're implemented by different teams. Now, some people argue that for very complicated algorithms that are very, very difficult to implement, different teams may still fail at the same point for very difficult algorithms, but it's still a safer choice than homogeneous, but it is a lot more expensive. And this is where I really want to get to. Just create safe requirements. Ultimately, everything we talked about, identifying the hazards, looking at the potential faults, determining the potential workarounds, all lead to additional requirements in your requirements document. That's really what we're here for, is understanding what goes into the requirements document. So this process that I showed you, which you will be essentially mandated to go through, that I showed you earlier, walks you through hazard identification, fault analysis, using fault trees, and ultimately into the requirements document. Okay, I'm gonna so that's my ending slide. The rest of this is just beyond the scope of this course, but we could take this into a lot more discussion. I have this safety critical class that I teach, a lot more details about how you would design it and implement it and test it, but that's beyond the scope. We're going to stop here because all we're interested in is making sure we get the right requirements, okay? Make sense? So, okay. So, homework, homework 2, I believe, is on this topic. So you can actually, if you want to, you can do homework 1 and 2 if you want. But I gave you an extra week. I'm defining a safety critical system here. I'll let you read through it. It's software controlling this industrial press. A lot of software, industrial, robots, systems that control automation like this. Very, very big area for software. Industrial systems control everything these days. It's amazing how much software is really controlling these industrial systems. So this is just one example of this. It's a safety critical system. What I want you to do, I give you a couple high-level requirements, but what I want you to do after I describe some of the sensors, remember how that example I showed you earlier showed a sensor and how that sensor could fail in that hazard analysis. So here's some sensors that tell when certain things happen, like the cover is opened and closed, etc. And what I want you to do is, based on this sensor and a brief description of this system, I want you to go off and create a fault tree. And some of the things in the fault tree that could cause faults, the things at the leaves, okay, could come right out of this table. But I want you to think through the problem a little bit, and then I want you to create a fault tree. And then based on your fault tree that you build up, I want you to recommend what additional requirements would you add to a requirements document to maybe, all those options, obviate, redundancy, what would you propose as a new requirement to make that system safer, okay? It's a good practical problem. Try it. You'll have fun with it. Not too difficult. So that's homework number 2. All right. I also out online. So far, we good? Homework 1, homework 2. Not overwhelmed yet, right? Okay. Because you have 2 weeks to do them, or 1 week, next week, and then the week after. Now, this project, before I get into this, this is a semester-long project, so you're going to have the whole semester. So I asked you to do a lot of things in this project, some of which you may not even recognize what they are, but that's okay. I'll just go through it quick. But every topic we're going to talk about in class. So if you show up to class, everything I'm asking you to do, you're going to be able to, we're going to have a lecture on it, okay? So basically what I'm asking you to do, pick one of these hypothetical systems, and I've got, I think, 5 of them in here. This one's a game, a computer game. I'm not going to read through every one of these. You can do that. One of them is an autonomous vehicle, getting really big these days. Google, even the automakers are doing a lot with autonomous vehicles. You can have a lot of, that's a safety critical system. A telematics system for automobile. Telematics dealing with, nav systems and radios and all that kind of stuff. All that stuff you find in the middle. I have a big description of telematics in here if you want to read through that. GPS, all that, A police command and control system, kind of a wireless type system, distributed system if you want to look at distributed systems. Talk about that. A fire and security alarm monitoring system. This is more of a event-driven system. I talk about that. A management conferencing system. Okay. Now, if you want to pick something else, you can do that too, but send me a proposal. You can either pick one of those or send me a proposal for what you want to do. I said you can have project teams. You can work on it individually or up to, at least you can go up to 3 people. If you get the 4 or more, let me know. I may give you a few more things to do with team sizes of 4, but 1, 2, 3, you're good. Find your team, whatever. Now, the deliverables, ultimately, what I'm going to grade is what you submit at the end of the semester. If you want to submit any work in progress, you can do that. I'll look at it, give you feedback, but I won't grade it. You can take advantage of that if you want to do that as well. It starts with an introduction. So I've given you a very brief introduction, but what I'd like you to do is do a little bit more research and come up with a nice introduction as if you were presenting it to a client. Okay? Maybe a page or 2 of, take what I've given you. There's a lot more information online. You can put some pictures in there, do whatever. I gave you a couple of questions to answer that would normally go into, if I was going to a client with this kind of proposal, these are some of the questions I'd like to have in my little introduction, okay? Okay, remember that 5-step process? We talked about it last week, and we talked about constraints tonight. I gave you there's a specific slide in your notes on this topic. You can go off and do that, okay? This one we're going to talk about next week, frame diagrams. It's a way of framing the problem, and we'll talk all about that next week. A context diagram, and then we're going to do some modeling. By the way, again, if you don't understand what these are, we're going to have a lecture on every one of them. We're going to create some data models, so for IT systems, that'll be very important. We're going to do some use cases, both normal and abnormal scenarios, and I'm going to introduce something called the misuse case. These are for when someone's trying to hack into a system. If you've got security requirements, this would be a very important thing. We'll do some UML diagrams. If you're familiar with UML, I'm not going to teach a UML class per se, but I'm going to pull bits and pieces of these models out. And so we'll do some work with activity and sequence diagrams. If you've got a data transformation system, where data is flowing through a system and transforming as it goes, producing different reports and stuff like that, data flow diagrams are important. We're going to talk about data flow. Requirements sometimes have formal methods. Now, if I teach you a formal method, it's a very mathematical approach. It'll take all semester just to do it. So I'm not going to do that, but we'll go over some basics. But instead of I'm going to teach you a more practical, semi-formal method for specifying event-driven systems. You'll have a lot of fun with it. It's called sequence enumeration. We're going to do that. We're going to build a prototype of the system. Okay, every one of the projects that I've given you is going to have some user interface. So we're going to prototype. I'll teach you how to do that. And then you're going to write your requirements, and I'll talk more about how to write the functional and non-functional requirements. You can see there it is, language. We dealt with that tonight, right? You can actually start doing some of this if you like, or looking at it anyway. And then we'll do some decision tables, structure analysis. We'll do all of our traceability. And then because I'm going to want you to really prove to yourself that you have good requirements, I'm going to ask you to take a subset of those requirements and explain to me how you're going to test it and know whether you've implemented it. So I'm going to turn you into a tester to prove that you've got the right requirements, like I said earlier tonight, okay? And then a bibliography and a glossary. Now, if this seems like a lot, it's really not, because you're going to have till Christmas to do it, almost. So a lot of this information are things you would find in professional requirement specifications. So we'll go through this step by step, and at the end we'll have this requirement specification that you can actually give to a design team, and they can actually go off and build your system. And this is, again, this will take us the semester, but we'll do it kind of a divide and conquer approach and get through it all. If you keep up, you should have no problem with it. If you wait till Thanksgiving holiday, you might have a little bit of a problem with it, okay? And believe me, I can tell the difference when I get a project. The ones that started on Thanksgiving break and the ones that started earlier. It's pretty obvious. So try to keep up. Any questions on any of that stuff? I know it's a lot, but believe me, it's not that. I mean, the project, it's not going to be that difficult to get through it. Again, you can work in a team. So you can, if you have a team, the only thing I'll ask with your team is that you, make sure everyone's contributing. There's a lot of nuances with people traveling and stuff like that. Try to make sure you come up with a model where everyone's contributing to the project if you have a team. And if you have if you have another choice, send it to me. I'll review it and get back to you. Any questions on anything tonight? You all good? See you next time? All right. Thanks. I'll let you guys go. Thanks for bearing with me for nonstop talking for a couple hours straight, but now you're free to go.